Something is hiding in the darkness of space, and it might not be what we think. For decades, physicists have told us that when a massive star dies, it collapses into a black hole, a point of infinite density where space and time break down, where the laws of physics as we know them simply stop working. But what if that story is incomplete? What if there's another possibility, one that doesn't require the universe to tear itself apart at the seams? In the year 2001, two physicists named Powell Mazer and Emil Motola proposed something radical. They suggested that what we've been calling black holes might actually be something else entirely. These objects would look almost identical to black holes from the outside. They would bend light, warp space, and pull matter toward them with the same terrifying gravitational grip. But on the inside, instead of a singularity, instead of that impossible point where density becomes infinite and our equations spit out nonsense, there would be something far stranger and yet somehow more reasonable, a core made of dark energy. They called these objects gravastars, short for gravitational vacuum stars. And if they exist, they would solve one of the deepest problems in all of physics. To understand why gravastars matter, we first need to understand the problem they're trying to solve. When Albert Einstein published his general theory of relativity in 1915, he gave humanity a completely new way of understanding gravity. Gravity wasn't a force pulling objects together across empty space. Instead, gravity was the curvature of space-time itself. Massive objects bend the fabric of the universe around them, and other objects follow those curves. The Earth doesn't pull you toward its surface. Rather, the Earth bends space-time in such a way that the natural path forward through time also happens to be a path toward the Earth's center. This was a revolutionary idea, and it made predictions that seemed almost magical. Einstein's equations predicted that light would bend around massive objects, that time would slow down in strong gravitational fields, that the universe itself could expand or contract. All of these predictions have been confirmed with extraordinary precision. But Einstein's equations also predicted something troubling. They predicted that if you took enough mass and compressed it into a small enough space, the curvature of space-time will become so extreme that nothing, not even light, could escape. The mass would collapse inward without limit, crushing down to a single point of zero volume and infinite density. This point is what we call a singularity. Einstein himself was deeply uncomfortable with this prediction. A singularity is essentially a place where the mathematics breaks down completely. Infinite density doesn't make physical sense. It's not a description of reality. It's a confession that our theory has reached its limits, that we've pushed our equations into territory where they can no longer tell us anything meaningful. For a long time, physicists hoped that singularities were just mathematical curiosities, artifacts of overly simplified models that would disappear when you added more realistic physics. But in the 1960s, Roger Penrose and Stephen Hawking proved a series of theorems showing that singularities weren't accidents. They were inevitable. If general relativity was correct, and if a star collapsed past a certain point, nothing could stop it from forming a singularity. The universe seemed to demand that these impossible objects exist. This created what physicists call the singularity problem, and it remains unsolved to this day. We have overwhelming evidence that black holes exist, We've detected gravitational waves from black hole mergers. We've imaged the shadows of supermassive black holes at the centers of galaxies. We've watched stars orbit invisible massive objects at speeds that can only be explained by extreme gravitational fields. But we have no way of knowing what's actually happening inside these objects. The event horizon, that boundary beyond which light cannot escape, acts as a perfect curtain, hiding whatever lies within from the rest of the universe. This is where Gravastars enter the story. Mazur and Motola asked a simple but profound question. What if the collapse never actually completes? What if something intervenes to stop the formation of a singularity, creating instead a stable object that looks like a black hole from the outside, but has a completely different internal structure? The key to their proposal is dark energy. This is the mysterious substance that makes up roughly 68% of the total energy content of the universe. We discovered dark energy in 1998 when astronomers measuring distant supernovae found something shocking. The expansion of the universe wasn't slowing down as everyone expected. It was speeding up. Something was pushing the cosmos apart, counteracting the attractive pull of gravity on the largest scales. Dark energy is strange because it has negative pressure. In ordinary materials, pressure pushes outward. If you compress a gas, it pushes back against you. But dark energy works in the opposite direction. Its pressure is negative, which in the context of general relativity means it creates a repulsive gravitational effect. This is what drives the accelerating expansion of the universe. Mazur and Motola realized that if you could somehow create a region of space filled with dark energy at the center of a collapsing star, this negative pressure would push outward against the inward pull of gravity. If the conditions were right, these two forces could balance perfectly, preventing the collapse from continuing and avoiding the formation of a singularity entirely. The structure they proposed has 3 distinct layers. At the very center is the dark energy core. This region is filled with what physicists call a gravitational vacuum condensate, a state of matter where the vacuum energy becomes extremely large and negative. This core exerts an enormous outward pressure. Surrounding the core is a thin shell of ultra-relativistic matter. This shell is incredibly dense and incredibly thin, with matter compressed to densities beyond anything we can create in laboratories on Earth. The shell is what gives the Gravistar its mass, and it sits in a delicate equilibrium, balanced between the outward pressure from the dark energy core and the inward pull of its own gravity. Finally, on the outside is ordinary empty space, curved by the mass of the shell, just as space would be curved around a black hole of the same mass. The remarkable thing about this structure is that from the outside, it would be nearly indistinguishable from a black hole. The space-time geometry in the exterior region would be identical to the Schwarzschild geometry that describes non-rotating black holes. Light passing near a Gravistar would bend in exactly the same way. Orbiting objects would follow the same trajectories. The gravitational pull would be the same, but there would be crucial differences. A Gravistar has a physical surface, the outer edge of that thin shell. It's not a one-way membrane like an event horizon. In principle, an object falling toward a Gravistar could stop before reaching the shell, or even bounce off it. A black hole, by contrast, has no surface, only the event horizon. and anything crossing that boundary is forever lost to the outside universe. This distinction might seem academic, but it has profound implications for physics. Black holes have an information problem. When matter falls into a black hole, the information about what that matter was made of seems to disappear. Stephen Hawking showed that black holes slowly evaporate through a process called Hawking radiation, and this radiation appears to be completely random, carrying no information about what fell in. This leads to what's called the black hole information paradox, a fundamental conflict between quantum mechanics, which says information cannot be destroyed, and general relativity, which says black holes destroy information. Gravastars could solve this problem because they don't have true event horizons. Information that falls onto a Gravastar's shell could, in principle, eventually be released back into the universe. The shell might ring like a bell when struck by infalling matter, emitting gravitational waves that encode information about what fell in. There would be no paradox because there would be no information loss. Let's go deeper into the physics of how a gravastar actually forms. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The outward pressure from nuclear fusion reactions in the core, which has held the star up for millions or billions of years, suddenly disappears. The core begins to collapse. For stars of moderate mass, this collapse is halted by quantum mechanical effects. Electrons resist being squeezed too close together due to something called the Pauli exclusion principle. This resistance creates a pressure called electron degeneracy pressure, which can support a white dwarf against further collapse. If the star is more massive, even electron degeneracy pressure isn't enough. The core collapses further until protons and electrons combine to form neutrons. Neutron degeneracy pressure can then halt the collapse, creating a neutron star. But for the most massive stars, even neutron degeneracy pressure fails. According to conventional physics, nothing can stop the collapse at this point, and the star forms a black hole with a singularity at its center. Mazur and Mottola proposed that something different happens during this final stage of collapse. As the matter becomes increasingly compressed and approaches the densities at which a black hole would form, a phase transition occurs. A phase transition is a sudden change in the properties of matter, like water freezing into ice or boiling into steam. In this case, the phase transition transforms ordinary matter into a gravitational vacuum condensate. The vacuum energy, which in normal space is tiny and positive, becomes enormous and negative. This is the dark energy core. The matter that was collapsing doesn't actually cross an event horizon. Instead, it settles into the thin shell surrounding the dark energy core, held in equilibrium by the balance of forces. The physics behind this phase transition is speculative, but not unreasonable. We know that vacuum energy exists. It's been measured in the Casimir effect, where two metal plates placed very close together experience a tiny attractive force due to quantum fluctuations in the vacuum between them. We also know that vacuum energy can be affected by extreme conditions. In the very early universe, during the epoch of cosmic inflation, the vacuum energy was enormously larger than it is today, driving a period of exponential expansion. Mazur and Mottola suggested that the extreme conditions inside a collapsing star might trigger a similar transition, creating a region where the vacuum energy becomes negative and large enough to halt the collapse. Now we come to the most recent and perhaps most fascinating development in gravastar theory. In 2023, physicists Daniel Jampolsky and Luciano Retzala at Goethe University Frankfurt published a paper describing what they called nesstars, from the Russian word for nested dolls, matryoshka. They found that the equations of general relativity allow for gravastars to be nested inside one another, like those famous wooden dolls where each one contains a smaller one inside. A nestar would have multiple concentric shells, each separating a dark energy core from the next layer outward. You could have a small gravastar inside a larger gravastar inside an even larger one. The mathematics allows for an arbitrary number of these nested layers, limited only by the total mass and radius of the outermost structure. This discovery emerged from a careful mathematical analysis of the boundary conditions at each interface between shells and dark energy regions. Jampolsky and Retzala showed that stable configurations exist where each shell is held in equilibrium by the dark energy pressure from inside and the gravitational pull from outside. The shells don't collapse into each other, and the overall structure remains stable. What's particularly intriguing about nestars is what happens when they form or when they merge with other compact objects. When matter falls onto a nestar, it doesn't simply add to the existing structure. Under certain conditions, it can trigger the formation of a new outer shell, adding another layer to the nested structure. Similarly, when two nestars merge, the result isn't necessarily a single object, but could be a more complex nested configuration. This has implications for gravitational wave astronomy. When black holes merge, they produce gravitational waves with a characteristic pattern that depends on the masses and spins of the merging objects. The final moments of the merger, called the ring down, occur when a newly formed black hole settles into its final state. The frequency and damping of the ring down are determined entirely by the mass and spin of the final black hole. If gravastars or nestars exist instead of black holes, the ring down would be different. The merged object would have additional vibration modes corresponding to oscillations of the shells. These modes could persist for longer and might have different frequencies than black hole ring down modes. With sensitive enough gravitational wave detectors, we might be able to distinguish between black holes and gravastars by carefully analyzing the gravitational waves from merger events. The LIGO and Virgo collaborations have already detected dozens of compact object mergers, and so far, all the observations are consistent with standard black hole physics. But the precision isn't yet high enough to definitively rule out alternatives like gravastars. Future detectors, including the space-based LISA mission scheduled for launch in the 2030s, will have much greater sensitivity and might finally answer this question. There's another observational signature that could potentially distinguish gravastars from black holes: echoes. When a gravitational wave signal reaches Earth from a black hole merger, it arrives as a single burst of waves. But if gravastars exist, the wave might partially reflect off the surface of the gravistar shell. This reflected wave would then bounce around inside before escaping, producing a series of echoes following the main signal. In 2016, physicist Giada Betty and colleagues claim to have found evidence for such echoes in LIGO data. This claim remains highly controversial, with other researchers arguing that the signals are consistent with statistical noise. The debate continues, and the existence or absence of echoes remains an open question. Let's step back and consider the broader context of what gravastars represent. They're part of a long tradition in physics of proposing alternatives to singularities. Einstein himself spent decades trying to find ways around the singularities in his own theory. Other physicists have proposed different alternatives, including regular black holes, which replace the singularity with a smooth core, and fuzzballs, which emerge from string theory and suggest that black holes are actually tangled balls of strings with no interior at all. What makes gravastars particularly appealing is their relative simplicity. They emerge from classical general relativity without requiring new physics beyond what we already know exists. Dark energy is real. Negative pressure is real. Phase transitions are real. Gravastars simply combine these ingredients in a new way. Critics of the gravastar hypothesis point to several potential problems. One concern is stability. The thin shell of matter is under enormous stress, squeezed between the dark energy core and its own gravity. Small perturbations could potentially cause the shell to collapse or explode. Detailed calculations have shown that at least some gravastar configurations are stable against small perturbations, but questions remain about whether gravastars can survive the violent processes that would create them. Another concern is the formation mechanism. The standard picture of black hole formation is straightforward. Matter collapses and nothing stops it. For a gravastar to form instead, something must trigger the phase transition that creates the dark energy core at exactly the right moment. What physical process causes this transition? Why doesn't it happen earlier or later? These questions don't have clear answers yet. There's also the question of angular momentum. Real collapsing stars rotate, and the objects they produce must conserve that angular momentum. Rotating black holes, described by the Kerr solution to Einstein's equations, are well understood. Rotating gravastars are much more complicated. Some work has been done on this problem, but a complete understanding of rotating gravastars remains elusive. Despite these challenges, gravastars remain a viable and intriguing possibility. They represent the kind of creative thinking that pushes science forward. Even if gravastars turn out not to exist, studying them forces us to confront deep questions about the nature of gravity, space-time, and the limits of our theories. The story of dark energy itself is one of the strangest in all of physics. When Einstein first developed general relativity, he added a term to his equations called the cosmological constant. This term represented a kind of built-in energy of empty space, and Einstein included it because he wanted his equations to describe a static universe that neither expanded nor contracted. When Edwin Hubble discovered in 1929 that the universe was actually expanding, Einstein famously called the cosmological constant his greatest blunder. He removed it from his equations, and for decades, physicists assumed it was zero. Then came 1998. Two independent teams of astronomers, the Supernova Cosmology Project and the HISE Supernova Search Team, were measuring the distances to faraway type Ia supernovae. These supernovae are remarkable because they all have roughly the same intrinsic brightness. By comparing how bright they appear to how bright they should be, astronomers can calculate how far away they are. What both teams found was shocking. The distant supernovae were fainter than expected, meaning they were farther away than they should be if the universe's expansion was slowing down or even continuing at a constant rate. The only explanation was that the expansion was accelerating. Something was pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos. This something is what we now call dark energy. It behaves exactly like Einstein's cosmological constant, a constant energy density throughout all of space that creates repulsive gravity. The observation earned the team leaders the 2011 Nobel Prize in Physics. But here's the puzzle. When we try to calculate the cosmological constant from fundamental physics, we get an answer that's wrong by a factor of about 10 to the power of 120. This is the largest discrepancy between theory and observation in all of science. It's called the cosmological constant problem, and nobody knows how to solve it. Some physicists believe the solution might lie in a better understanding of how quantum mechanics and gravity interact. Our current theory of quantum gravity, to the extent that we have one, predicts that empty space should be seething with quantum fluctuations. These fluctuations carry energy, and that energy should curve space-time. But the calculated energy is astronomically larger than what we observe. One speculative idea is that there might be different phases of the vacuum, just as water can exist as ice, liquid, or steam. Perhaps the vacuum we live in is in a particular phase with a small positive cosmological constant, while other phases could have much larger values, positive or negative. This is exactly the kind of physics that gravastars depend on. The dark energy core of a gravistar is essentially a region where the vacuum is in a different phase, one with large negative pressure. If we understood vacuum energy better, we might understand whether such phases are possible and under what conditions they could form. The connection between gravastars and cosmology runs even deeper. The same dark energy that might stabilize gravastars is also responsible for the ultimate fate of the universe. If dark energy remains constant as the universe expands, as current observations suggest, the cosmos will continue to accelerate forever. Distant galaxies will recede from us faster and faster, eventually disappearing beyond our cosmic horizon. The universe will become increasingly cold, dark, and empty, a future sometimes called the Big Freeze. But if dark energy can change, if the vacuum can transition between different phases, the future might be very different. A sudden transition to a different vacuum state could release enormous energy, potentially destroying everything in the cosmos. This scenario is called vacuum decay, and while it seems unlikely, we can't rule it out. Gravastars, if they exist, might be natural laboratories for studying these extreme vacuum physics. They will be places in the universe where the vacuum has already transitioned to a different state. Studying their properties could give us clues about the nature of dark energy and the possible fates of the cosmos. Let's talk about what it would be like to approach a gravistar. From a great distance, you wouldn't notice anything different from a black hole. The space-time curvature would be identical. Your instruments would measure the same gravitational field. Light from stars behind the gravistar would bend around it in the same way, creating the same distortions and brightening. As you got closer, things would start to diverge. Approaching a black hole, you would eventually cross the event horizon. This is a one-way journey. Once you cross, you're committed to falling inward, no matter what you do. If the black hole is small, the tidal forces would tear you apart long before you reach the singularity. If it's large enough, like the supermassive black holes at the centers of galaxies, you might cross the horizon without even noticing, only to be inexorably drawn toward the singularity. Approaching a gravistar, there's no event horizon to cross. As you get close to the shell, you would feel the gravitational pull intensify, but you could still turn around and escape if you had enough thrust. If you actually reach the shell, you would encounter matter at densities far beyond anything in ordinary experience. The shell is thin but incredibly massive, and the conditions there are extreme beyond comprehension. What happens if you hit the shell depends on details we don't fully understand. The shell might absorb you, adding your mass to its own, or you might be destroyed by the extreme conditions. Or perhaps, in some configurations, you could pass through. The physics of a shell is complicated and depends on its composition and structure. One thing is certain: you would not encounter a singularity. There's no point of infinite density inside a gravistar. The dark energy core has finite density and occupies a finite volume. It's strange, certainly, filled with negative pressure and exotic vacuum energy, but it's not a breakdown of physics. The equations remain valid. The universe makes sense. This might seem like a small thing, but it's actually profound. The existence of singularities in our best theory of gravity has troubled physicists for over a century. Singularities are places where the theory fails to make predictions. They represent the limits of our knowledge, points beyond which we cannot see. If gravastars exist instead of black holes, there would be no singularities in the universe. General relativity would be complete and consistent, describing everything without breaking down anywhere. Of course, we don't know if gravastars exist. The question is ultimately empirical. Nature will tell us one way or another. Our job as scientists is to figure out how to ask the question, to design observations and experiments that can distinguish between the possibilities. The Event Horizon Telescope, which captured the famous image of the black hole shadow in the galaxy M87 in 2019, provides one avenue. The shadow is the dark region surrounded by the bright ring of glowing gas. For a black hole, this shadow has a specific size and shape determined by the event horizon. For a gravistar, the shadow would be similar but not identical, potentially with subtle differences in its exact size or shape, depending on the properties of the shell. The current images aren't precise enough to detect these differences, but the Event Horizon Telescope is constantly improving. Future observations with more telescopes spread across the globe, or even with telescopes in space, could achieve the precision needed to test whether what we're seeing is really a black hole or something else. Gravitational wave observations provide another avenue. As mentioned earlier, the ring-down signal following a merger could differ between black holes and gravastars. Additionally, the in-spiral signal, the pattern of waves produced as two objects spiral toward each other before merging, might show differences if the object have surfaces rather than event horizons. When neutron stars merge, the collision produces characteristic signals because the stars have physical surfaces that smash together. Black hole mergers don't produce these signals because there's nothing to collide. The horizons simply merge smoothly. Gravistar mergers might show intermediate behavior. with some surface effects but different from neutron stars. The ultimate test might come from objects that are right at the boundary between neutron stars and black holes. There's a maximum mass that a neutron star can have, beyond which it must collapse into a black hole. This limit is somewhere around 2 to 3 solar masses, though the exact value depends on the equation of state of neutron star matter, which we don't know precisely. If we observe compact objects in this mass range, their properties could tell us what happens when neutron degeneracy pressure fails. Do they become black holes with singularities? Or do they become gravastars with dark energy cores? Careful observations of such objects could answer this question. The discovery of gravitational waves has opened a new window on the universe, and we're still in the early days of gravitational wave astronomy. The first detection came in September 2015, when LIGO observed 2 black holes merging about 1.3 billion light-years away. Since then, dozens more events have been detected, including mergers of black holes with black holes, neutron stars with neutron stars, and possibly black holes with neutron stars. Each detection teaches us something new about the universe. We've learned that black holes can be heavier than we thought, with some detected black holes having masses of 80 or even 100 times the mass of the Sun. We've confirmed that gravitational waves travel at the speed of light, as Einstein predicted. We've used the neutron-star merger detected in 2017 to help measure the expansion rate of the universe. Future detectors will push even further. The Einstein Telescope and Cosmic Explorer are proposed ground-based detectors much larger and more sensitive than LIGO. LISA will observe gravitational waves from space, sensitive to different frequencies and able to detect sources that ground-based detectors can't see. The pulsar timing array projects are already detecting the gravitational wave background from millions of supermassive black hole mergers throughout cosmic history. All of these observations will help us understand what compact objects really are. Are they black holes with singularities? Gravastars with dark energy cores? Nesstars with multiple nested shells? Fuzzballs made of strings? Something else we haven't thought of yet? The answer matters for our understanding of gravity, quantum mechanics, and the fundamental nature of space-time. Black hole singularities are often described as places where general relativity meets quantum mechanics, where both theories must be important, but where they conflict with each other. Understanding what really happens in these extreme environments could give us clues about how to reconcile the two great pillars of 20th century physics. Let me tell you about some of the theoretical work that supports the Gravastar hypothesis. After Mazur and Motola's original 2001 paper, other physicists took up the idea and explored its implications in greater detail. Physicists have studied the stability of gravastars, asking whether these objects can maintain their equilibrium against perturbations. The answer turns out to be yes, at least for certain configurations. There are stable solutions where the shell is in equilibrium and returns to that equilibrium after being disturbed. Not all configurations are stable, but some are, which is enough to make gravastars plausible. Other work has explored how gravastars would form. This is trickier because you need a mechanism that produces the phase transition, creating the dark energy core at exactly the right moment. Several proposals exist, including transitions triggered by quantum effects when matter is compressed to extreme densities, and transitions related to the information processing that must occur during collapse to avoid the information paradox. The thermodynamics of gravastars has also been studied. Black holes have thermodynamic properties, including temperature and entropy. Hawking showed that black holes radiate with a temperature inversely proportional to their mass, and Bekenstein showed that black holes have entropy proportional to the area of their event horizons. These discoveries led to the holographic principle, the idea that the information content of a region of space is determined by the area of its boundary rather than its volume. Gravastars also have thermodynamic properties, but they're different from black holes. The surface of a gravistar isn't a horizon, it's a physical shell. The entropy is associated with the shell rather than an area, and it scales differently with mass. These differences could have observable consequences if we ever develop ways to measure the thermodynamic properties of compact objects. The mathematics of gravastars in more general contexts has been explored as well. What about electrically charged gravastars? What about gravastars and theories that modify general relativity? What about gravastars in higher dimensional spacetimes? All of these questions have been studied, and in many cases, gravistar solutions exist and are stable. This breadth of theoretical work gives confidence that gravastars are at least consistent possibilities within known physics. They're not ad hoc constructions designed just to avoid singularities. They emerge naturally from the mathematics of general relativity when you allow for the possibility of negative pressure matter. The philosophical implications of gravastars are worth considering too. If black holes with singularities exist, they represent a fundamental limit to human knowledge. We can never know what happens inside a black hole because no information can escape. The singularity is hidden behind the horizon forever. Some physicists have embraced this, arguing that perhaps nature really does contain unknowable secrets. Others have been troubled by it, seeing singularities as failures of our theories rather than features of reality. Einstein was in this second camp. He spent his later years searching unsuccessfully for a theory that would eliminate singularities. If gravastars exist instead of black holes, there are no fundamental limits to knowledge imposed by gravity. The universe is completely predictable, at least in principle. Every region of space-time can be described by equations that remain valid and finite. This doesn't mean we can actually observe everything. The universe is vast, and much lies beyond our horizon. But there's no place where physics itself breaks down. This connects to deeper questions about the nature of scientific theories. Should we expect our theories to be complete, describing everything without exceptions? Or should we expect them to have limits, domains of validity beyond which they fail? The history of physics shows both patterns. Newtonian mechanics is incredibly accurate, but fails at very high speeds and in very strong gravitational fields. Quantum mechanics is incredibly accurate, but we still don't understand some of its foundational puzzles. General relativity is incredibly accurate, but appears to predict its own failure at singularities. Gravastars offer a way for general relativity to be complete, at least for describing gravity in a macroscopic world. They show that the singularities might be artifacts of oversimplified assumptions, not fundamental features of reality. This would make general relativity more like electromagnetism, a theory that describes its domain completely without breaking down anywhere. Of course, Even if gravastars eliminate singularities, we still don't have a quantum theory of gravity. The reconciliation of quantum mechanics and general relativity remains one of the great unsolved problems in physics. But eliminating singularities would change the nature of the problem. Instead of asking how quantum effects resolve infinities, we would ask how quantum effects modify the structure of gravastars. That's a different question, possibly an easier one. Let me describe some of the cutting-edge research on nesstars in more detail. Jampolsky and Retsala's 2023 paper opened up a new chapter in gravastar physics by showing that nested structures are mathematically possible. The key insight is that each interface between a dark energy region and a matter shell must satisfy certain boundary conditions. These conditions relate the pressure and density on either side of the interface, ensuring that forces balance and the structure remains stable. Jampolsky and Retsala showed that you can have multiple interfaces, each satisfying these conditions, creating a layered structure. The innermost layer would be a dark energy core, just like in a simple gravastar. Surrounding this will be a thin shell of matter. Then there would be another dark energy region, then another shell, and so on. The outermost region would be ordinary empty space, curved by the total mass of all the shells. The number of layers isn't fixed. You could have a nestar with 2 shells, or 3, or 10, or more. The mathematics allows for any number, though practical constraints would limit how many layers could actually form. What determines the number of layers? This likely depends on the formation history. A nestar that formed from the gradual accumulation of matter might have many layers, each one added when enough matter accumulated to trigger the formation of a new shell. A nestar formed from a merger of simpler gravastars might inherit the layers of its progenitors, potentially creating complex multi-layered structures. The observational signatures of nestars would be even more distinctive than simple gravastars. Each shell would have its own oscillation modes, creating a richer spectrum of gravitational wave signals. The ring down following a nestar merger could show multiple frequencies corresponding to vibrations of the different layers. There's also the possibility of resonances between the layers. If the oscillation frequency of one shell matches a harmonic of another, energy could transfer between them, creating complex dynamic behavior. This could lead to distinctive signals that would be unmistakable evidence for nested structure. Jampolsky and Retsala titled their paper "Hairy Black Holes Without Singularities and Nested Matryoshka Structures." The word hairy refers to another aspect of their work. The no-hair theorem is a famous result in black hole physics, stating that black holes are completely characterized by just 3 parameters: mass, charge, and angular momentum. All other information about what formed the black hole is lost. The black hole has no hair that could tell you about its history. Gravastars and nestars violate this theorem. They have additional structure, the shells and cores, that represents extra information beyond mass, charge, and spin. In this sense, they are hairy, with properties that depend on their formation history and internal structure. This has implications for the information paradox. If black holes have no hair, then when matter falls in, the information about that matter seems to be lost. But if the objects are really gravastars or nestars with hair, the information isn't lost at all, It's encoded in the structure of the shells and cores. The apparent loss of information was an illusion caused by our incorrect assumption that these objects were black holes. I want to spend some time discussing the dark energy core in more detail, because this is the most exotic and counterintuitive aspect of gravastars. What exactly is a region of space-time filled with dark energy, and how does it behave? In general relativity, the source of gravity is described by something called the stress energy tensor. This mathematical object encodes the energy density, pressure, and momentum flux of matter and radiation at each point in space-time. For ordinary matter, the energy density is positive and the pressure is either zero or positive, depending on whether the matter is cold or hot. Dark energy is different. Its stress energy tensor has a peculiar form: positive energy density, but negative pressure. Moreover, the magnitude of the pressure equals the energy density, but with opposite sign. This relationship means that as the universe expands and the volume increases, the total amount of dark energy increases too. It's not like ordinary matter, which gets diluted as space expands. This sounds like it violates conservation of energy, but it doesn't. In general relativity, energy conservation is more subtle than in Newtonian physics. When space itself is expanding, the energy in the gravitational field changes, and total energy is conserved only when you include this gravitational contribution. Dark energy is consistent with this more nuanced version of energy conservation. In a gravastar, the dark energy core would be a region where this exotic equation of state holds. The negative pressure pushes outward, opposing the inward pull of gravity from the surrounding shell. If the pressure is large enough and negative enough, it can completely balance gravity, creating a stable equilibrium. What would it be like inside the dark energy core? This is speculative, but we can make some educated guesses based on the physics. The core would be smooth and homogeneous, with the same properties at every point. There would be no matter in the conventional sense, just the quantum vacuum in its unusual negative pressure state. Time would pass differently inside the core. In regions of strong gravitational fields, time slows down. This is gravitational time dilation, and it's been confirmed countless times by experiments. The dark energy core would be in a region of intense gravitational potential, so time would run slower than time far away. But unlike inside a black hole, the difference wouldn't be infinite. There's no singularity, no place where time stops entirely. Light could propagate through the core, though it would be affected by the curved space-time. If you shone a flashlight from one side of the core to the other, the beam would follow a curved path determined by the space-time geometry. Someone watching from outside would see the light taking a long time to cross because of time dilation, but it would eventually emerge. All of this assumes that our extrapolation of known physics is correct. The dark energy core is a region of conditions far beyond anything we can create or study in laboratories. Quantum effects that are negligible under ordinary conditions might become important. The vacuum might behave in ways we don't predict. There could be surprises. This uncertainty is part of why gravastars are interesting. They're predictions of general relativity applied in extreme conditions. If we can observe gravastars or rule them out, we learn something about whether general relativity remains valid in those conditions. Either way, we advance our understanding.